Hello everyone, welcome back to the course on measurement and instrumentation, and we are in the week 7 and today is lecture number 4 for this particular week. We are discussing transducers, and in the transducer we started our discussion on strain gauges, and we have seen various kind of strain gauges in our previous lecture, which was lecture number 3 for this 7th week discussion, right? We have seen a number of strain gauges, and if you broadly classify them, whatever classification we have seen, the broader classification could be in this form. You can have bonded strain gauges, you can have unbonded strain gauges, and depending on how these gauges are fabricated, you can have thin film strain gauges, and for higher sensitivity we have semiconductor strain gauges. Okay, let's see the construction of some of these gauges and how they basically work, and this will give you a proper idea that how you can extend the usability of these strain gauges for various application, including measurement of strain, measurement of pressure, etc. Okay, so in the series, let's first learn about unbonded metal strain gauges. We are taking the example of this unbonded metal strain gauges because these are conventionally utilized as a transducer. Okay, so they have a natural application in transducer. Okay, so as the name suggested, unbonded metal strain means this is the strain gauge is actually unbound to the area where actually the strain is going to be measured. Okay, and let's see that how they are segregated and how basically the measurement takes place. Okay, but before we actually jump into the discussion on how the measurement takes place, just see the construction of a unbonded metal strain gauge. Okay, so unbonded metal strain gauge is shown over here. You can see that this has the strain gauge windings. So this is 1 and 2 windings, and you have another winding, strain gauge winding 3 and 4. Okay, this 1 and 2 and 3 and 4 are very important because they are utilized in the form of mostly in Wheatstone bridge, and these numbers we will recall there. Okay, you have spring element and force rod is there, and on top you have diaphragm where actually any kind of pressure or whatever you are measuring is actually applied. Okay, now this gauge consists of a wire which is stretched between 2 points in a insulating medium. This insulating medium is important, and mostly air itself can act as a good insulating medium. So this arrangement you can also imagine inside a normal ambient air. Okay, the wire, their configuration is very important, and mostly these wires are not pure metallic, but mostly they are alloys. Okay, like a copper nickel alloy, a chrome nickel alloy. Okay, then we have nickel iron alloys. So mostly these 3 forms of alloys are preferred for this unbonded metal strain gauges, and this is because of various reasons. The first is say low temperature coefficient of resistance for these wires. This will ensure reduced thermal errors associated with the heating of these wires. Okay, you have high electrical stability associated with these alloys, and most important, these wires for the unbonded metal strain gauge is the linear relationship between the resistance and the strain. Okay, so for these alloys you have perfectly or near to perfect linear relationship between the resistance and strain, and that's why they are preferred over their metal counterparts. Okay, they also have high elastic limits. Okay, means that they returns to original length after the strain is removed. Okay, they have good fatigue strength for repeated loading, and mostly these transducers are actually repetitively loaded, and that's why good fatigue strength is required. Okay, then these devices require low hysteresis, and these alloys ensure the low hysteresis associated with the wires. Okay, they also have better corrosion and oxidation resistance, and they have higher resistivity as compared to their metal counterparts, and this allows a compact design, means a shorter length wire can do the work. Okay, So they also have long-term measurement reliability and improved accuracy and repeatability as compared to the metal wires. Okay, the typical thickness of this wire is about 0.003 mm. So they are particularly in diameter. Okay, means that they are very thin. Okay, and since they are metal wires, their gauge factors are around little higher than 2 because they are alloys, not exactly metal. So anything between 2 to 4 is desired. Okay, and they can sustain a force of about 2 millinewton and so. Okay, and the length of the wire is about 25 mm or even less than that if you have a better alloy. Okay, the flexure element is connected via a rod, as I have mentioned, to a diaphragm. Okay, this is the rod I am talking about. Okay, now this diaphragm is the element which is exposed to the pressure. So you are not applying any pressure directly to the wires, you are applying to this diaphragm. Okay, now the wires are tensioned to avoid buckling when they experience any compressive force. Okay, so already tension exists in the wires. Okay, the unbonded metal wire gauges employ preloaded resistance wire connected in a Wheatstone bridge, as you can see over here. Okay, and that's exactly why I was talking about the strain gauge windings 1 and 2 and strain gauge windings 3 and 4, which are acting as a resistance R1, R2, R3, R4. Okay, so at initial preload, the strains and resistances of the 4 arms are normally equal, and when you have equal resistances, you know that Wheatstone bridge is balanced, means that the output voltage of the bridge is 0. Okay, now when you have any pressure applied to the diaphragm, okay, this will produce a small displacement of the order of 0.004 mm, which is actually the full scale. Okay, now the displacement increases tension in 2 wires. Okay, and at the same time other 2 wires will have decreased tension. Okay, so when you have this kind of configuration where you have increased tension or decreased tension in 2 wire or increased tension in other 2 wire, means that you have a condition where you have resistance increment in 2 wires while there is a decrement in the resistance in other 2 wires. Okay, so increase the resistance of 2 wires which are in tension, while the resistance of the remaining 2 wires will decrease. Okay, and when you have this kind of imbalance condition, means that your bridge is actually not in the balanced condition, and at that particular point you cannot expect E naught to be 0, means that there is certain voltage at the output, means that at that particular event you have E naught not equal to 0. Okay, now whatever voltage you have at the output, the E naught, okay, it will be proportional to the input displacement, and the input displacement is actually directly proportional to the pressure. So whatever output voltage you are getting is actually indicating the applied pressure. Okay, so this is how a unbonded metal wire strain gauge actually works without being attached or without being bonded to the actual pressure system. Okay, now if you see, the sensitivity of these devices are not very high. Okay, because the gauge factors are limited in this case. So for higher sensitivity, you will require a material or a strain gauge which has better gauge factors, and usually this desire is fulfilled by semiconductor strain gauges. Means that semiconductor strain gauge can basically provide you a higher sensitivity because they have a higher value of gauge factor. Okay, so a high gauge factor basically means a relatively greater change in resistance, which can be easily measured with good degree of accuracy. So if you remember the definition of gauge factor, we have seen that delta R by R divided by the strain was the gauge factor, right? So a higher gauge factor means that a relatively greater change in the resistance, which can be easily measured with a good degree of accuracy, and it does not only affect the accuracy, but it also affect other parameters like resolution and so. Okay, so semiconductor strain gauges are very helpful for these kind of conditions, and even you can have more compact strain gauges formed by these semiconductor strain gauges, because you can use modern technologies like MEMS technology or CMOS technology to fabricate this kind of devices. Okay, the resistance of semiconductor changes with the change in the applied strain, and unlike in the case of metallic gauge where the change in the resistance is mainly due to change in the dimensions when strained, the semiconductor strain gauge depends for their action upon the piezo-resistive effect a lot. Means that the change in the value of resistance is due to not only the change in the length and change in the area, but it heavily depends on the change in the resistivity of the material. Okay. So, semiconducting materials such as silicon and germanium are used as resistive materials for semiconducting strain gauges, and a typical strain gauge, semiconducting strain gauge consists of a strain sensitive crystal material in the form of semiconducting material and leads, mostly in the form of metallic leads, okay, which are sandwiched in a protective matrix. Okay. The production of these gauges employs conventional semiconductor technology, as I have mentioned, using semiconductor wafers or filaments which are thickness of the order of 0.05 mm or so, depending on the various other factors like what is the diameter of the wafer and so on. So usually these silicon wafers come in the dimensions like you have in laboratory, you have 2-inch wafers, you have 3-inch wafers, 4-inch wafers, 6-inch wafers, then 8-inch wafers, and now the industry follow like 200 mm, 300 mm and so on. So depending on the diameter also, the thickness of these wafers varies, okay, and then these semiconductor strain gauges are bonded on a suitable insulating substrate, for example on Teflon, okay. So gold leads are generally employed, as I have mentioned, for making the contacts, and some of the typical semiconductor strain gauges are shown over here. You can see that you have a base material, and on top you have this semiconductor strain gauge, and then these are bonded by these pads. Okay, so these are the terminals that I was talking about. Okay, mostly the metallic terminals. Okay. Now you can use this semiconductor strain gauge to construct a pressure transducer. Okay. If you see in general, a pressure transducer will require two fundamental components for its construction. The first is a plate or membrane whose area actually okay, and you also require a detector that will require to the applied force. So basically what you are detecting is the force, and we know that the pressure can be calculated by the applied force to the known area. So basically if you know this force and know the diaphragm area, you can calculate the applied pressure, and that's how exactly the pressure transducer, the semiconductor pressure transducer works. Okay. Now advantage is both the components, I mean the diaphragm or the plate or the membrane, whatever you want to call, and the detector, both can be fabricated using popular semiconducting materials like silicon. Okay. So a silicon diaphragm pressure transducer consists of a thin silicon diaphragm as an elastic material, and at the same time a piezo resistance made up of again doped silicon is also used. So this is a typical example of silicon diaphragm pressure transducer, and you can see that this has been made by back etching a silicon substrate. Okay. The piezo-resistive gauge resistors made by diffusive impurities are also made on the same diaphragm to make the piezo resistances, okay, at the two sides to measure the applied pressure. Okay. And these impurities can be diffused to these points by, I mean there are various ways of doping silicon. You have two general methods for doping silicon. You have either you can dope by diffusion, and you can dope it also by ion implantation. Okay. So diffusion is mostly a temperature driven process where you have thermal gradient and you have a concentration gradient also, and because of this temperature changes, the concentration gradient also, this will diffuse and get implant in this. And you know that silicon is a group 4 element, okay, and this is very popular that group 3 elements like boron, okay, and similarly group 5 elements, okay, elements can be doped. And if you are doping a group 3 element in silicon, okay, you can call it p-type silicon, and when you are doping group 5 element, you are actually making a n-type silicon or n-type silicon semiconductor. So these are very basic views of how silicon can be doped, but there are detailed courses on doping of silicon, and basically you will find these things in a semiconductor physics courses, okay. So I will suggest that for this particular topic, if you are interested in more detailed discussion, I will suggest that you check with any good semiconductor physics book, okay, and see that how these dopings can be done, okay. And if you are not interested in doping and all, for this particular course, I am just mentioning that the piezo-resistive gauge resistors are formed at these two particular terminals, okay, or two particular sides of this silicon semiconductor by certain doping technique. And as I have mentioned, there are two ways of doping a silicon. You have diffusion, okay, and then you have ion implantation. All right. Again, there are different kind of diffusion also, and that is again beyond the scope of this particular course to discuss. So we'll converge here to only discuss our semiconductor strain gauges, okay. Now, single crystal silicon has very superior elastic characteristic, and that's why exactly you are able to use it as a diaphragm also, okay. So there is virtually no creep and no hysteresis that occurs even under strong static pressure. So even you have very strong static pressure, then also you will not find any kind of hysteresis or any kind of creep, okay. The gauge factor of silicon is many times higher than that of the thin metallic conductors, and that's why initially mentioned that when you want higher sensitivity, you have to go for semiconductor strain gauges like strain gauges based on silicon, okay. The gauge factor of silicon, as I have mentioned, is many times higher than that of metal conductors, okay. And again, this becomes even more higher when you talk about extrinsic silicon, means that when you have doped it. So when I say intrinsic silicon, means that it is not doped, okay. Intrinsic silicon and extrinsic silicon means that here when I say intrinsic silicon, means that it is not doped, okay, and here it is doped. Either you have made a p-type silicon, okay, or you have made a n-type silicon, all right. So even for p-type and n-type, you have different gauge factors, okay. And gauge factor, if you remember, we have defined it earlier, this GF was equal to del R by R, which was the per unit change in resistance, and this was the mechanical strain per unit change in the length, right. And if I compare the semiconductor strain gauge against the standard metal strain gauges, you can see this list. I mean, this may be not exact, but very near to what the values or ranges are. For metal foil strain gauges, the gauge factor is in the order of 2 to 5, while for thin film metals, you have a gauge factor of the order of 2. For thick film resistors, the gauge factor is of the order of 100, while for semiconductor strain gauges, the gauge factor is anything in the range of 50 to 200, while for p-type silicon and n-type silicon, you have ranges from 100 to 170, while for n-type, it is of the order of minus 100 to minus 140. P-type germanium has a gauge factor of 102, while for n-type germanium, it is around minus 150. For single crystal silicon, it is around minus 125 to 200, while for polysilicon, means polycrystalline silicon, it is of the order of plus minus 30, okay. So when stress is applied to a semiconductor resistors having initial resistance say R, the piezo-resistive effect results in the change in this resistance R as del R by R equal to pi L into sigma L plus pi T into sigma T. In this equation, this pi L and sigma L are, longitudinal piezo-resistive coefficient, this pi L and pi T are the piezo-resistive coefficient in a longitudinal and transverse directions, while this sigma L and sigma T are the stresses in longitudinal and transverse directions. Okay. So, del R by R is equal to pi L into sigma L plus pi T into sigma T. I am calling this equation 1. Now, the pi coefficient here depends on the orientation of the resistors of the silicon crystal. Okay. Mathematically, the piezo-resistivity can be described by 6-vector notation. We will not go in detail, but the stress vectors sigma, say I am calling having a base say lambda to just denote it, like sigma lambda is like 0, 1, 2 and so on. Okay. The stress vector sigma is connected via the piezo-resistivity tensor pi k lambda, where k lambda is again can be 0, 1, 0, 2 or say 1, 0 and so on. Okay. So, the stress vector sigma is connected via the piezo-resistivity tensor pi to the change in the resistivity vector del rho, okay, where the base is k and k is again from 0 to 6, okay, like in this form. So, del rho by rho naught is equal to pi into sigma, okay, where the lambda can vary from 1 to 6, okay, and accordingly you can have value of rho. So, this gives you a better idea. So, del rho omega by rho lambda 1 to 6 pi omega lambda into sigma lambda, where lambda again vary from this is 1 to 6, okay. So, 1 to 6, this omega lambda again lambda varies from 1 to 6 and this is for one particular omega, okay. Fine. So, the coefficients are approximately denoted as pi L and pi T, and pi L is equal to minus pi T, and this is equal to either pi L or minus pi T is equal to half of pi 4,4. Pi 4,4 is very important in case of silicon, because pi 4,4 is the piezo-resistive coefficient defined along the silicon crystallographic axes, okay. And the piezo-resistive coefficient pi for p-type and n-type materials are related to the n number of factors, including the level of doping impurity concentration, the crystallographic orientation of the material, temperature of operation and type of the conductivity, okay. Now, due to the cubic crystal structure of silicon, the piezo-resistivity tensor has only 3 independent components, which are pi 11, pi 12 and pi 4,4, and therefore, the tensor can be written as pi k lambda equal to pi 11, pi 12, pi 12, pi 12, pi 11, pi 12 and pi 12, pi 12, pi 11, okay, and all components are 0 except this pi 4,4, okay, fine. So, we have 3 independent components, pi 11, pi 12 and pi 4,4 for the case of silicon, okay. Now, in p-type silicon, the piezo-resistivity tensor component pi 4,4 is about 2 magnitude larger than the other 2 components. Hence, the component pi 4,4 has the main impact on the resistivity change due to the applied stress, okay. And a change in the resistivity is proportional to the applied stress and subsequently to the applied pressure, and that is how you quantify for the applied pressure. So, delta R1 by R1 that initially we have seen is equal to minus del R2 by R2, which is equal to half of pi 4,4 sigma 1y minus sigma 1x. So, if you know these quantities, you can calculate this delta R1 by R1, and once you know this, you can calculate the applied pressures also. Okay. The resistors are positioned on the diaphragm in such a manner as to have the longitudinal and transverse coefficient of the opposite polarities, and that is why this the placements of R1 and R2 are like this, okay, and that is why this equation is valid, del R1 by R1 equal to minus del R2 by R2 to take care about the longitudinal and the transverse strains, okay, or say stresses, okay. So, that is how you can use semiconductor strain gauges to calculate the applied pressure, of course, in turn by first calculating the change in the resistance, okay. Now, this is what you have seen for bonded semiconductor strain gauges. Similarly, you can have bonded metal wire strain gauges and again metal thin film strain gauges also, but we are taking an example of metal wire strain gauges, and this is a typical example you can see. Okay, the bonded metal wire strain gauges are used for two purposes. One is for stress analysis and also for the construction of the transducers. Okay. So, a resistance wire strain gauge consists of a grid of fine resistance wire of about 0.025 mm in diameter, or it can be even less than that. Okay. Now, the grid is cemented to carrier, which is also known as base, which may be thin sheet of paper or a thin sheet of bakelite or even a thin sheet of Teflon, as was in the case of semiconductor bonded strain gauges. Okay. A number of base materials are available like epoxy, bakelite, cellulose or fiberglass materials, and again they have temperature ranges in which you have to operate. Okay. So, epoxy has certain range, bakelite cellulose has separate range, and fiberglass materials has a separate range for continuous operation. Okay. And if you go for higher temperature, everyone comes with the limited operation ranges. Alright. So, if you see, what you have done is you have glued this wire grid to the carrier base, and by measuring any change in the resistance, you are calculating the strain or say applied pressure on it. Okay. Similarly, in place of wires, you can also have thin films. There are number of ways to coat a very conformal thin film of metals like nickel and so on. Okay. You can have sputtering. I mean, there are n number of physical vapor deposition techniques like sputtering. You can have thermal evaporation. You can have E-beam evaporation. Okay, you can have PLDs, a pulse laser deposition, and so on. So, by all these techniques, actually, you can get the strain gauges. Okay. Ultimately, as an end user, what we have to do is we have to select one out of the strain gauges that are available. Okay. And this will solely depend on the sensitivity requirement. Of course, there are other parameters like the temperature range of operation that we have just seen. Okay, you may have requirement of like either you are trying to measure say static strain or dynamic strain, or it also depend on environmental exposure to the strain gauges. Okay, and ultimately it will also depend on the budget in which you want to get these strain gauges, like semiconductor strain gauges comes at little higher cost as compared to the other strain gauges that we have seen, but then it have several advantages, particularly in terms of sensitivity requirement of the end user and so on, right. So, this is in very brief what is strain gauge and how you can use them in various measurement. Okay. Maybe in the next class, which will be the 5th lecture of our 7th week, okay, we will try to discuss the new transducer maybe for the measurement of temperature. Okay, and then after that maybe we can discuss some more transduction techniques. Thank you.